Okay, let's start here. Thanks.
Okay, very good. So, hello folks, this is your friendly neighborhood virtualization co-chair, and it's my pleasure to introduce the final invited speaker of the main POPL conference, who is Alexandra Silva. She recently joined Cornell as faculty and was previously faculty at University College London and Radboud University. And some of you might know her as member of the steering committee of PLMW, which the Programming Languages Mentoring Workshop, which I think has brought a lot of participants to POPL this year and many other years. We're all used to playing the game of guess which conference is going to be the big grand reopening where everyone shows up and says hello to each other again. It wasn't quite POPL this year, but Alexandra is also the general chair for the Federated Logic Conference this summer, so maybe you'll be able to see her there, even though this is a virtual session. She's done a lot of work in subjects like automata and linear algebra, including with applications to networks. And I understand one grand unifying theme is co-algebra, which she is going to be telling us about in this presentation. Take it away, Alexandra.
Thanks so much, Adam, for the kind introduction. And yeah, I hope to see many of you in the near future. Maybe the PLDI will be in person, or maybe at FLOC, which indeed is a big federated conference, and hopefully we'll gather many people who will make it to Israel. So it is a great honor to be here today. I am sad that I'm not in Philadelphia. Still, it's a great honor to have been invited to give a keynote. So thanks for the invitation and for the opportunity to speak to the community. I'm originally not, I did not do my PhD inside the PL community. So I did my PhD in category theory and co-algebra. And I then sort of joined the PL community a bit later in my career, and that makes it an even bigger honor to be here today and to be able to talk a little bit about this intersection between my previous life and my current life, if you like. So what I'm going to do, I'm going to start with a brief history of co-algebra and co-induction, and how the field sort of emerged and how things evolved along the decades, and then how that's went into programming languages. And we see these days a lot of papers at POPL and even at PLDI that use coalgebraic techniques. I want to reflect a little bit how we got here and where we go from here. So if you look at co-algebra and co-induction, and you try to look for the source and where things started, I think it's fair to say that a lot of the early work goes back to the 70s to the work of Arbib and Mains. So Michael Arbib and Ernest Mains, who are here in the slide, they were working in trying to understand structures in control theory and in dynamic systems. And they wrote a long sequence of papers on the use of category theory and greatest fixed points and co-algebra to have a uniform framework of dynamical systems and automata. And this was sort of a very popular activity in the 70s. And they, as I said, they have a range of papers. It's sometimes hard to keep track of how many papers they wrote on the topic. Then later, in the early 80s, mid 80s, Robin Milner was working on his work on processes, and he had his work on CCS. And around the 81, 82, he was working with David Park, who is someone who was very prominent in the theory of fixed points and also in concurrency theory, and sadly passed away a few years after this. But so David Park was on sabbatical in Edinburgh, where Robin Milner was at the time. And he was reading Robin's book on CCS, and at that time he found what has become a famous mistake in Milner's earlier work. And in Milner's own words, David Park came down during breakfast one morning and carried his CCS book and told him that there's something wrong. And Milner was preparing to defend himself and to argue that that his definition of observational equivalence for processes was actually correct, and he had done that definition inductively. But David pointed out to Robin that the non-co-inductive way, which was the inductive way, that he had set up observational equivalence didn't quite reach the maximal fixed point, which was what Milner then argued later in that work. And so Milner took that comment and then realized he was right and got excited about co-inductive proof techniques. And so around that time, I think it became more mainstream that co-induction and greatest fixed pointers started playing a role in the theory of processes. Also in the 80s, Arbib and Mains consolidated a lot of their work in the 70s and some other work they did in the early 80s and wrote a book. That book was called Algebraic Approaches to Program Semantics. I don't think it's a very well-known book, perhaps in this community, but it's a really, I find it's a really foundational piece of work. And if you look through the table of contents of this book, you will recognize a lot of the things that have become mainstream theory of PL. So for instance, early in the book, in chapter one is dedicated to the notational semantics, and they study a fragment of Pascal, and they talk about partial additive semantics and so on. And then later on in chapter 3, they look at data types, and already back then they were looking at data types as functors, and they were looking at fixed points of functors, and they were studying both the least and the greatest fixed point of a functor and showing how that was a good way to think about data types and to reason about data types. So this book sort of is not super well known, but it has actually a lot of interesting material that then made it to mainstream PL theory. And also at the very end of the 80s came what some people would say is the paper that really founded the field of co-algebra. It's a paper by Peter Axel and Max Mendler called the Final Co-algebra Theorem. And it was published at the Category Theory Conference in 1989. But really, it started this whole field of co-algebra. And one thing I would like to mention is that Max Mendler had just finished his PhD at Cornell before he joined Axel as a postdoc. And he was working throughout his PhD, he worked in the theorem prover New Pearl, which many people in this community know. And back in the 80s, he implemented in New Pearl co-induction and co-inductive reasoning. And New Pearl is perhaps not one of the mainstream theorem provers that we see these days, but it has a great support for co-induction precisely because Mendler implemented it very early on in its development. So yeah, I think it's fair to say that in the 80s, a lot of the work where co-induction and co-algebra was playing a key role was a lot in this theory of processes that Milner pioneered, and in concurrency theory, and in the development of the notion of bisimulation as a greatest fixed point and type theory in the work of Mendler and others. And then, as I said, that paper of Axel and Mendler really spearheaded the field. And in the 90s, we saw a lot of the sort of foundational papers of co-algebra coming out, and Jan Rutten and Bart Jacobs were fundamental in these efforts, and they started also the workshop on co-algebraic methods in computer science. And since then, we have seen much more work on the development of co-algebra and co-induction. And really, in the 90s, the message that the researchers working on this wanted to pass was that co-algebra and co-induction was the right mathematics to study state-based systems. And state-based systems here are to be interpreted as some general descriptor of anything that has states and transitions. So for instance, a control flow graph of a program, or a data flow graph, an automaton, a dynamical system, etc. So this was sort of the brief history of co-algebra until the end of the 90s, when the workshop on co-algebraic methods, the first edition was 1998. And then I did an exercise. I was curious, when did the word coalgebra and co-induction first make it to POPL? So I kind of went deep into the digital library and spent some time looking to see if I could find some of the early papers. It's interesting that the earliest paper I could find was a paper in POPL'97 that explicitly mentioned co-induction. It was a paper on infinitary control flow analysis. And again, here you start seeing this state-based theme sort of emerging. So you're looking at the analysis of control flow, and then it is a natural place to use greatest fixed points in this analysis, and therefore it is a natural place to use co-induction. And the same applies to another paper in '98 by Xavier Leroy that has a whole section on the co-inductive proof principle that they use to prove security properties of this type applets, and goes on again explaining the connection to greatest fixed points, but how co-induction is a neat formalization of this principle. And I'll mention one more paper from 2000 by Andrew Appel and Amy Felty on a model of types and machine instructions for proof carrying code. So all these papers, they appeared at POPL around the time that coalgebra as a field was really becoming solid. As I said, the first conference on coalgebraic methods happened around this time as well. But there was clearly, from researchers working in particular in type theory and in flow analysis, there was a clear bridge between these two communities, and the techniques from co-induction were making their way into mainstream programming languages. Now, as I told you, I did my PhD on coalgebra. My thesis was called Clini Coalgebras. It was about automata and coalgebra. And I never imagined moving more to the PL side of the world. But what really sort of changed things for me, there are two papers, and I would like to briefly mention them. So around 2012, I think this published 2012, before this paper was published, actually, I saw a print of this paper called The Marriage of Bisimulations and Cryptological Relations. It's a paper by Gil Hoare, Derek Dreyer, Georg Neis, and Victor Vafeadis. And the first thing, the thing that attracted me to this paper, I will not lie, was the title. I saw bisimulation in the title, and I thought, oh, that's cool. And then I went on reading it, and it was beautifully written, and there was this really nice use of bisimulations, and it suddenly hit me that maybe some of the techniques I had been studying had a home at a conference like POPL. And what really solidified that feeling was then another paper that actually appeared the year after, but I heard about this before it appeared at POPL, which is a paper on co-patterns, a paper by Brigitte, Pientka, Andrea Zabel, and collaborators. And this paper on co-patterns I found extremely beautiful, the way they were using ideas from co-induction to sort of improve support in a programming language. And at that time, I was also working, or I had been working with Dexter Kozen and Jean-Baptiste Janine on trying to have better co-inductive support in OCaml. And so this paper was really, for me, brought home that maybe I belonged at least part-time in this community. And I'll mention two more papers that are related to what I will talk next in my talk. Paper by Fritz Heingolein and Lars Nielsen, and the paper by Filippo Bonchi and Damien Puz. And let me spend just a couple of seconds on this last paper. So this last paper on checking non-deterministic automata equivalence with bisimulations up to congruence is a paper that theoretically might look very simple. But in fact, the way that they derived this new algorithm for non-deterministic automata came from a general framework that I worked together with Damian, Filippo, and Jurgen Roth, and some other people on up to techniques for co-algebras. And the fact that they took that very abstract framework and they managed to instantiate it to an example, which was non-deterministic automata, and then sort of, this is the point that was for me really inspiring, and then brought that into an algorithmic perspective that showed that abstract technique actually gave you the foundations to develop a really efficient equivalence algorithm that behaved better than any other algorithm that had been tailor-made for non-deterministic automata. I think that was really very cool. It's a really nice paper. It's a really nice tutorial if you want to learn about the principles of bisimulations up to. For me, this was, I think, one paper that changed my view on how much simple techniques can sometimes help in achieving algorithmic improvements. So, as a brief summary of what I was talking up to now, we went through a little bit of history of how coalgebra sort of evolved as a field since the 70s, and I mentioned this last paper from 2015. I mean, there's been many other papers at POPL since then, but this paper I find is a sort of a point in time that showed how these coalgebraic techniques can actually improve algorithms. So I think it's a really cool paper. And throughout this historical perspective and also the description of this paper, at the center of a lot of this is a structure that we all know and love, which is automata. And automata play, a role in verification and in semantics of programming languages. And they are also sort of the star when you try to show the value of coalgebraic techniques. And the reason for that is that automata come in many different shapes and forms. And depending on what you want to do with a certain automaton, you will see different types play a key role. And those types can be very simple, from plain deterministic automata to non-deterministic to weighted automata, tree automata, probabilistic automata. There's a range of types of automata that get more and more complex and allow you to carry out more and more interesting verification tasks. But what is interesting is that a lot of the times when we have a new automaton, say even for quantum computing, a new paradigm that has seen the development of quantum automata and models of computation there. When you have a new type, you might end up asking the same questions over and over again. So you might ask, what type of semantics do I have here? So what type of languages do I accept or recognize? Is it a language of words, of traces, or is it a language of trees? Or what is the behavior of this automaton? Then often we ask the question of equivalence. Can I actually answer? Is it decidable, and is it decidable in an efficient way that two automata have the same behavior, accept the same language, assign the same probability to every word, etc. And then there's a question how to use these structures, these automata, in verification. And sometimes that question can be answered by equivalence, and there are many verification tasks that you can actually reduce to equivalence questions. Sometimes you want to do other things like model checking and other techniques. But you ask this question over and over again, right? So you have a new type of automaton, and then you ask the question, and you answer the same question over and over again. And the idea behind the use of coalgebra and co-induction in automata, and this idea, as I said, goes back all the way to the 70s to Arbib and Mains, is that these questions should be possible to have uniform and parametric answers to all these questions. We should be able to capture what the behavior of an automaton is in a parametric way. We shouldn't have to sort of prove and reprove the same things over and over again. And so what plays a key role in developing these uniform and parametric answers in co-algebra and co-induction is that of a functor. And I will explain later what a functor is. But basically, the idea is that every automaton or every automaton type can be captured by a functor, and then this functor can be used to, in a uniform and parametric way, provide a toolkit for that type of automaton. So in particular, from the functor, you are able to modularly derive a syntax to specify behaviors, a semantics, both the notational and operational. And perhaps more interestingly, you are able to derive algorithms that allow you to reason about equivalence. And if your functor comes with some extra structure, you can also derive up-to techniques. So these up-to techniques are techniques to enhance the bisimulation method or the equivalence method to give you more efficient algorithms. And all of these can be achieved just from the functor type. The functor also, interestingly, allows you to connect your syntax and your semantics and allows you to translate from one side to the other. And what do I mean by this? Let's look at an example, and that's how I'm gonna basically illustrate all these components in this slide. Think of deterministic automata or regular languages, if you like. There is a functor, which I will show you in a moment, that captures regular languages. And that functor is what underlies the syntax of regular expressions. And it is also what underlies the fact that the operational semantics of regular expressions is given by automata. And there's this cornerstone theorem that goes back to the 50s by Stephen Kleene that says that every regular expression and every regular language are connected in a unique way. And there is a one-to-one correspondence between the behaviors you can syntactically represent as regular expressions and semantically represent as regular languages and accept by deterministic automata. And so the proof of that theorem and this connection can actually be captured by the functor. And it is all the things that you see here in the slide in red is all derivable from the functor. Of course, you know, the theory of formal languages and all we know about regular languages and many things you know about regular languages were developed completely independently. But you can study them from this perspective, and that can give new insights, which I want to show you later. So what I will do next, I will go a bit technical for a few minutes, and I'll sort of show you how this picture instantiates for the case of regular languages, and how what is a functor, what does the functor look like, and how does that functor actually connects to regular expressions and all the other elements in this slide. You will see this slide coming back through the rest of my talk, because I want to frame the message of my talk very much on this slide and on the fact that at the core of coalgebraic techniques and at the core of using coalgebraic techniques in PL is really the fact that if I'm given a functor in a certain setting, I can, from the functor, learn a lot about the behaviors that are happening in that setting. And that setting can be the semantics of a programming language, can be a verification task, can be many, many things. And so I want to really try to bring home this idea that the functor is at the center of a lot of the results that you can derive. So what is a functor? So a functor is a transformation on a category. A category is a collection of objects and arrows. So think, for instance, the category of sets and functions. So sets are the objects, and the functions are the arrows in this category. So the key thing about the arrows in the category is that these arrows have to compose. So you have to be able to take an arrow from an object X to Y, and then another arrow from an object Y to Z, and you have to be able to compose them. And for every object, there's a special arrow called the identity function. And the identity function basically sends an object to itself. And so examples of categories are the category of sets and functions, the category of sets and relations. So relations are the arrows in this case, the category of vector spaces and linear maps. So the objects are vector spaces and the arrows are linear maps between these vector spaces. And the functor is a transformation on this category, and it has to be defined both for objects and arrows. So a functor needs to map an object in the category to another object and needs to map an arrow to another arrow. And this mapping needs to satisfy certain laws. In particular, it should map the identity arrow to itself, and it should preserve composition. Let me make this a little bit more concrete and show you an example of a functor in the category of sets. So take a set B, a functor, a possible functor in the category of sets is the constant functor B that sends any set to the set B and sends any arrow to the identity function on B. So this is a functor that basically collapses everything into the set B. Another simple functor that you'll always have in any category is the identity functor that sends an object to itself and sends an arrow to itself as well. And you can compose these functors in certain ways. You can create Cartesian products, you can create co-products, etc. So think an algebraic data type. And the things you can do in an algebraic data type, you can most likely do, you can do in all functors in sets, but you can most likely do it in other categories as well. So now I have a category and I have a functor. And what is now a coalgebra and where does that lead us? So a coalgebra is going to be a pair of an object and a function from x to f of x that represents a transition dynamics. So let me go into this. So the functor is the transition type. So I have my object x, and I'm doing transitions in this object that have type of the functor f. And we'll see an example in a moment that makes this very concrete. The coalgebra is the collection, so it's this pair of the set of states and the transition function. And this pair, so the functor, together with the state, is indeed what is enough to then determine all the ingredients that I showed you in the previous slide. And as I said, I want to make this even more concrete by now showing you for a specific f, namely the f that captures regular languages. And the way I'm going to do this, I'm going to show you the definition of a deterministic automaton, and together we're going to recover what the f might be in that case, and then we're going to analyze how that instantiates to all the little boxes you see in this slide. So what is a deterministic automaton? Let's look at an example. A deterministic automaton is a set of states. In this case, on the slide here is a set with two states, x and y. And then there are two components to the transition of an automaton. On the one hand, I need to say for every state whether the state is final or not. So in the example here, x is a non-final state and y is a final state, which I mark with an underscore. And then for every letter in my alphabet, so in the example here, I'm considering a two-letter alphabet with A and B, I make a transition between the states. So if you stare at this automaton for a moment, you will see that the state x, if I take state x as my initial state, what I can do in state x, I can read traces that have an odd number of a's. So if I read an a, I end up in y, which is an accepting state, and then I can read many b's. If I read a second a, I'm back in x, which is non-accepting. So in order to accept, I need to go back to read a third a, etc. So there's these dynamics in this structure, in this automaton, that shows how to accept. And that dynamics can be fully represented by these two functions, the functions that tell me whether a state is final or not, and the function that tells me how to transition. So if I take those two functions together and I put them together into one function, which I can pair the results, I get a transition structure that takes my state space x and returns something that looks like a composite state. That is a pair that tells me whether my state is final or not and gives me the transitions for every letter in the alphabet. So here, what I've just done is showing you that in the category of sets, so here I'm working with sets and functions. In the category of sets, the functor 2 times x to the a is the transition structure of a deterministic automaton. So this is my functor. So now let's take this functor into the previous picture. So this is the picture. And now I'm going to put my functor at the center of my picture. And let's ask the question, what do I know now that I have this functor here? So first thing I know is that regular expressions are the right syntax to specify behaviors. And this is I put here on the slide, the usual syntax of regular expressions. If you would derive it directly from the functor, it might look slightly different, but it would be equivalent. And how do these connect really to the functor? Now, in regular expressions, we always have a 0 and a 1. The 0 is supposed to be there to denote the empty behavior, and the 1 is there to denote the state that only accepts the empty word. And those two syntactic expressions, 0 and 1, they are generated from the fact that my functor has this 2 in the output. So this is a direct connection. The fact that I have letters and sequential composition and the plus in regular expressions comes from the fact that I have these functions from A to X. So I need to specify a function that for every letter in the alphabet tells me my next state. And in order to do that, I need to know which letter I'm taking right now. That's why I need the A. And I need to know what I do next. That's the sequential composition. And I need to do that for every A and take the collection. And that's the plus that takes the union of all these behaviors. So I would have A sequentially composed with what happens after A, then plus B sequentially composed with what happens after B. So I've told you that 0, 1, and these other three expressions are connected to the functor. But there's also the star. Why is the star there? Why is the star in regular expressions? And the star is there because when I look at the transition type x to fx, if I want that transition to allow cycles, then I need the star. If I didn't have the star in regular expressions, and I look at what languages I generate from those regular expressions, you will see that the thing you have are finite trees. And so that would mean that the only thing you can specify are finite languages. And that would mean in terms of the automaton that you have no cycles. So if you want your automaton to have cycles, you need to add to your syntax some form of fixed point. And in the case of cleanest regular expressions, that was the star. Okay, so what else do I get from the functor? I get the notational semantics for most functors. And that, so in the case of this functor, are functions from A star to 2, which you will recognize are formal languages. Tell me for every word if a word is accepted or not. And what is that in relation to the functor? That is the final coalgebra. So the final coalgebra is an object that I will explain in the next slide that gives me a unique way to specify behaviors. So if I have a functor and if I have a coalgebra over this functor, a transition system of the type F, then the final coalgebra is a mathematical object in which every behavior of an F system can be mapped to. And that's why it is used as the notational semantics. And the operational semantics of regular expressions are given by automata, but in this specific case, they also come from the functor, and they are given by so-called Brzozowski derivatives, which again, I will also say a little bit more in the next slide. And all these things together really are coming from the functor. What else comes from the functor? The notion of F by simulation. And that is what gives me equivalence techniques. In order to get up to techniques, I need to have some extra structure that will be the up to structure. In the case of regular expressions, we do have equations between regular expressions. We know that certain regular expressions denote the same language, and we can use that fact in order to derive more efficient proofs. Now let's spend 1 minute or so on the final coalgebra. What is the final coalgebra, and why is it that it is important in semantics? So for every automaton, we know, for every finite automaton, we know that there is a unique to compute its regular language. And this is a fact that actually holds for most F coalgebras. So for an F coalgebra, for a large class of Fs, there exists the so-called final coalgebra, which is an object into which I can uniquely map every state. So in the case of the automaton, it tells me for every state here is the language that the state accepts. In the case of, say, weighted automata, it actually returns the weighted language that is, and that language has a vector space structure. And there are many, many examples like that. One particular automaton is that of expression. So through Brozovsky derivative, which gives this structure to the automata. And so if I replace, in this final coalgebra diagram, if I put my expression automaton there, which is the operational semantics of expressions, what do I get as a mapping for free from this diagram? And what I get, if I compute it, is exactly what the algebraic interpretation of regular expressions is in any standard textbook, which interprets the 0 as empty set and the 1 as the set with the empty word, and A as the singleton set, plus as union, etc. Okay, so this abstract perspective does yield as instances things we know from standard formal language theory. Now, let's go back to the diagram in which we have our final coalgebra and we have the automaton of expressions there. And what else do we have in this picture that will help in terms of? Well, I mentioned Klee's theorem, and Klee's theorem basically tells me that for any F coalgebra, or any finite automaton, any finite F coalgebra, I have a mapping into expressions. So I actually can derive an expression that represents the same language as that state accepts. And if you stare at these diagrams long enough, you might recognize that the commutativity of each of these diagrams actually gives rise to a system of equations about the states. And that system of equations that you can derive from these diagrams in general, not just for automata, but in general for an F coalgebra, that system of equations can be solved in many cases. And it is solving those equations that really gives rise to the proof of Klee's theorem. And that way of sort of expressing semantics and expressing the connection between semantics and syntax appears very prominently in Milner's work. And I would say that, the way that the correspondence between the behaviors of F coalgebra and syntactic expressions is very much equations in the way Milner pioneered in his work. We have more in this diagram. We actually have something between expressions and languages. So languages, you think of the semantic object, expressions are the syntactic object, and we have something in the middle. As I said, we know that many program equivalence equations hold between regular expressions. And that structure, so the equivalence classes of expressions, they form an automaton as well. And so they can also be put into this picture. And then, we have axiomatizations of regular expressions. Texer-Cozen has one. Conway has a bunch. There's a range of axiomatizations. And you can take any of those axiomatizations and basically express this object in the middle here, which is sort of in between syntax and semantics. And then proving completeness of such axiomatization amounts to a property of the unique map into the semantic object, which is injectivity, which is sort of a nice abstract way of looking at completeness. And so we have syntax in this diagram, we have semantics, we have denotational semantics through the final coalgebra, we have operational semantics through Brozovsky derivatives, and in the middle, in the axiomatization, we actually have the equivalence, and there are up to techniques coming from this axiomatization that can help you speed up the bisimulation proof. So I hope I've shown you a little bit through this example of deterministic automata and regular languages, how you take a functor and recover syntax and semantics and equivalence. And at this point, it would be fair to kind of stop me and say, okay, all these things are known and they are well known. And really, what comes first? Do you first know the functor and then get the syntax and the semantics? Do you first know the syntax and and then know the functor, and then know the semantics, or what in this picture has to come first? And that's sort of the beauty of these coalgebraic techniques, is that it doesn't quite matter what comes first. And in fact, I mean, really, in the end of the day, you know, it's a chicken and an egg, and things can be put together no matter what. And here's a very recent example of how this chicken and egg problem is not a problem. Back in 2015, there was a paper, which many people might know, on NetKAT, which is an extension of regular expressions to reason about networks. And that paper appeared in POPL'14. And in that paper, the NetKAT discovered the syntax and proposed the notational semantics. And here's a picture of the NetKAT carbon. And so that paper sort of ignored the coalgebraic aspect. It just sort of defined the syntax and proposed the semantics. And then a year later, we actually showed that, well, in fact, there's more to this story. And through the denotational semantics, we got the functor. And that functor was what then opened the door to a very efficient equivalence algorithm. And that's basically what then we proposed in POPL'15. But it was through this picture in which we went back to the functor and then derived the equivalence that sort of cleared up a lot of things. And it also showed us what the operator semantics should be. So in order to get all the ingredients that we wanted to have for this language, we really had to take a step back and look at the functor. And the fact that the syntax and the denotational semantics were there was nice, but not exactly essential in which order this was done. In the end of the day, we arrived at the full picture. And what is perhaps more interesting to say is that once we had the full picture with the functor and the syntax and all the semantics in place, we then could use that functor to go a bit further and generalize things. And that's how we then developed a probabilistic variant of NetKAT, because then we had a functor and we could play around with the functor and enrich it with probabilities and other things to derive more languages, more syntax, more semantics, more equivalence techniques. And this is sort of the power of harvesting coalgebraic techniques. Now, I would like to go back just briefly to my original slide on motivation for coalgebraic techniques, which had to do with this having automata in many shapes and forms. And I just want to briefly show you more functors, sort of say. So, you know, let's look at 4 types of these automata I had here. We saw deterministic automata. I showed you the functor. I showed you how you can derive things from it. Then weighted automata actually look very similar, but the functor now lives in a different category, which is the category of vector spaces and linear maps. And the same thing with probabilistic automata. It looks very close to deterministic automata, but the outputs are in the interval 0, 1, and it's a functor on convex spaces. And register automata look even more similar to deterministic automata, but they are in the category of nominal sets. And once you have these functors and these categories, you can then answer the questions on behavior, equivalence, etc., in a uniform way. And the categories, in particular vector spaces, convex sets, they do have algebraic structure. And that algebraic structure makes an appearance then in the equivalence algorithms and the up-to techniques. And by using these observations that these automata are sort of, you know, all of the same type, if you like, or a very similar type, we have managed to develop algorithms for different classes of automata based on algorithms we knew for deterministic ones. So in particular, one example is this POPL'17 paper on learning nominal automata, in which we showed that a classic learning algorithm for deterministic automata can be extended in a sort of principled way to nominal automata. I should say, you know, there's no free lunch. You still need to work towards developing the data structures that underlie the implementation and enable the algorithm in the right way. So there is work to be done, but there's this guiding light, which is given by the functor and by the coalgebraic technique that analyzes the algorithm. That's really the message. So I was talking a lot about automata and semantics to automata, and you might wonder, and beyond automata, what can I do? Well, you can do anything you can do with a functor. And the functor, in essence, really is you have a data type. Sometimes you have destructors, like you do in a coalgebra. Sometimes you have constructors, like you do in an algebra. Sometimes you have both. You have a mix of both. And for each, you have a functor that comes with certain destructors and constructors. What you want to do is basically recover the ingredients in this picture in a principled way. And here, if you only have destructors, you have a coalgebra, so you follow sort of the recipe I showed before using final coalgebras. If you have only constructors, then you're in a setting where you might have an initial algebra, and you can follow a very dual picture of what I showed you. But there are many flavors and data types and the way things go. And so here, it's really, once you have a functor in a situation where you're analyzing semantics of a program or maybe some verification task, the more important thing is to try to identify what structures are at play. Are there destructors? Are there constructors? Does my base category have algebraic properties that I can use? So there's all these ingredients that you need to spend some time identifying. And once you identify them, there are all these flavors of coalgebraic techniques, algebraic techniques, bi-algebraic techniques that you can use. And so I hope I've given you a little glimpse of how coalgebra can be used in programming languages. And if you're a programming language researcher trying to answer questions on equivalence, on behavior of programs, semantics, verification, having a toolkit around a functor is a good way to go. And I hope to have given you sort of glimpse of what this toolkit can give you if you have a functor, and how you can use that toolkit to go further. There's much more out there. A lot of this toolkit I showed you today is being used in different aspects of programming languages. I would say, in things where we have new paradigms like quantum computing, quantum programming languages, and we want to analyze new programs, this toolkit is a very useful guideline to how you can develop new algorithms and new semantic techniques. But also in more classical settings, I personally believe that this gives you a really good way to go about equivalence and verification. And I would like to conclude my talk with a quote that I heard at PLMW earlier in the week by Stephanie Weirish, who I greatly admire and like. And she said during a panel that, and this really rings with me. And I think my talk and this field of coalgebra and the intersection with PL is an example on how fruitful this conversation can be. So coalgebraic techniques were developed inside category theory in a more mathematical side of the world. And slowly they made their way to programming languages. And this is not a one-way street, it's really a two-way street. And the people doing coalgebra want to show other fields how they might want to use them, how they might want to use their techniques. But people from programming languages also have problems that they want solved, and they will inspire the people who are developing the more foundational techniques to work on those problems. And it is really this conversation that I think keeps the wheel turning. And I very much like to work at this intersection. I think it's very inspiring, and I hope to see many more people working at this intersection. I think POPL in the last few years has seen a lot of papers at the intersection of different fields. And I do think programming languages is one of the most welcoming fields in this sense. And we are all very open to this conversation. I think this is extremely fruitful and makes me very happy to be at POPL and at PL conferences. And with that, I would be very happy to take questions.
All right, thank you for the talk, Alexandra. And we have two text Q&A entries so far, and maybe I'll start by taking the highest voted one of those, and the folks in the room can try to manage their local data structure to see who might ask a question there next. So let's take the first virtual question. Kartik asks, are there tools available that one can use to make use of this technique in practice? So I'm sort of thinking of this as, is there the YAC equivalent tool that takes in a functor and builds other good stuff for us? Or is this all done only on paper / through human effort at the moment?
That's a good question, and there is. Let me see how I'm going to put this. There's some early tools. There's no like really very developed tool, but there is a tool that is part of the or is related to the K framework that Grigore Roșu works on. And there's a tool called Circ, which is on circular reasoning. And inside that tool, you can do part of the ingredients I showed you automatically. But there's also, there are also libraries for Coq, for NewPerl, for other established tools where fragments of what I showed are implemented. So I think the answer is there's no like the tool, but there are different like components here and there in different tools that one can use.
All right, thank you. Let's go to the next question. Question is whether there's an automata representation for NetKAT and prob NetKAT.
Yeah, so for NetKAT, there is an automata representation, which is in the POPL'22 paper, in the coalgebraic decision procedure paper. So that decision procedure is based on that automaton type. For prob NetKAT, there is an automaton representation for a fragment of the language, and that appears in a PLDI 19 paper called MacNetKAT, like McDonald's, but MacNetKAT. So that's, yeah. There is an automata representation for a fragment, not for the full language.
Got it. Do we have anyone wanting to ask a question in the room at the conference?
Hello. Thanks, Alexandra, for the great talk. I saw you presented the Wierzbowski derivative for going from a regular expression to an automata, and I'm aware that there's a similar thing for minimizing the automata. So if you go to the automata and then backwards again, I'm sure so I was wondering if there's a connection there between that idea and in gradient-based statistical learning, where you kind of repeatedly apply the derivative and to minimize a function. So I was wondering if you have a categorical explanation for that phenomena. Thank you.
Okay, thanks for the question. So a couple of things. So the Brozovsky derivative I mentioned gives indeed operational semantics to the regular expressions and produces an automaton. And that process is indeed iterative. So you apply the derivative over and over again until it's closed. And I say closed between quotes. I mean, at some point, you shouldn't hit any new regular expression in the process. And you have to be slightly careful when you do that. You have to apply the derivative modulo associativity, commutativity. And so there is a general version of that. So there is an understanding on how that works coalgebraically. And there's some work on using expressions from a functor and having these Brozovsky derivatives parametric on the functor. The algorithm you mentioned for minimizing, there's also a categorical explanation of that algorithm, which is not directly related to Brozovsky derivatives. So that algorithm is basically takes an automaton, reverses all the arrows, then takes the reachable part, reverses again, takes the reachable part, and magically you have the minimal automaton that accepts the same language. And indeed, there is a categorical view on that, and that categorical view yielded Brozovsky-like minimization algorithms for weighted automata, for quantum automata over the category of Hausdorff spaces and convex automata, etc. So there is indeed also there a categorical view.
We had another online question pop up in the meantime. Let's take a look at that one. So we heard quite a bit about using these techniques to study program behavior and equivalences, but what about the converse? Having support for co-algebraic structures built into languages. Do you have any insights there?
Yeah, so this question actually goes back to one of the papers I mentioned early on, for instance, on co-patterns. So co-patterns is an example of such support for coalgebra. The work I did on CoCaml is such an example as well, sort of extending OCaml to support more co-inductive definitions. There's a lot of work in the theorem proving community in COC and AGDA on extending the support for co-inductive reasoning and how you extend it without breaking the syntactic constraints that, for instance, they do have in COC. So I do think there is a stream of work that tries to increase the expressivity of languages and the language support in theorem provers.
Thank you. So we're at our scheduled ending time, but I think we could probably fit in maybe another question from the physical room. And also, if someone wants to ask a question, you might know there's a webcam facing at the audience. Wherever the last question asker stood, we didn't see the person on video. So if you stand in a slightly different place, we can have a more interactive experience for remote people. I don't know if there are questions left in the room. Maybe not. Webcam's not pointed in the right direction for me to be sure. Okay, so it sounds like we should probably, oh, I heard a sound. Don't know what it means. Yeah. Oh, there is one more online question though. Let's try that. You still have to do proofs in using these techniques. How much work is left when you have the generic stuff out of the way via these bigger results?
Yeah, that's a good question, and it's very sort of dependent on where you're applying things. So I can give you an example. I mentioned a paper on learning nominal automata, which was developing of a learning algorithm for nominal automata. So in that case, the abstract framework gave us the correctness of the algorithm for free. So the algorithm was there, was correct by construction, and then the work was in the implementation. So the base category was nominal sets. Programming languages in general don't offer native support to nominal sets, which are these. So nominal sets are infinite sets, but have a finite representation, if you like. This is the simplistic way I find of explaining them. And for those, so for that case, the work was basically in changing a language. We did it in Haskell.